So, good evening, everyone. Welcome to week 6 problem solving session of Analog Electronic Circuits course. We are halfway down with this particular session. So, today we'll be discussing about the problems based on current mirror circuits that we didn't discuss last time. So, starting with this question number 1. So, in this particular circuit, see what is given. It is given that NMOS has a VT of zero point 0.3 volts. Similarly, PMOS also has a VT of zero point 0.3 volts. Mu n Cox by 2 is 80 microsiemens per volt and mu p Cox by 2 is 40 microsiemens per volt. The supply voltage is 2.5 volts. Wn is 10 micrometers, Wp is 20 micrometers. L for all the devices is 1 micrometer. This R is 8.6 kilo ohms. And with this information, we have to find this current I. Okay. So now, first of all, let's analyze this particular circuit. Okay. So in this circuit, what can we observe? So this is gate, drain, source. Nitish, are you presenting something? So yeah, this presentation has stopped. Let me reshare again. Yeah, the screen is visible, right? Okay. So in this is drain and this is source. So if you observe very carefully, for this particular transistor, let's name them transistor 1, 2, 3, 4, 5 and 6. Okay. So for transistor 1, if you observe very carefully, your VGS is equal to VDS, right? And if you observe another
Diode
thing,
connected.
yeah, diode connected transistor, right? For 1. And for 2, if you observe, like VGS1 is equal to VGS2. And here, since nothing has been mentioned, so we'll consider these transistors as like ideal transistors, which means lambda is 0. So which provides us with the current formula of mu n Cox W by 2L VGS minus VTH whole square or VT whole square. The basic saturation formula, right? So in this one, now we know that the current only depends on VGS, right? So if for a transistor, the VGS matches and all other parameters will match, then the current will remain constant. Am I making sense? So let's say if a transistor, for example, the transistor 1 and 2, if you observe very carefully, the transistor 1 and 2 have VGS equal, they have their VT is equal, and mu n Cox W by 2L is also equal, right? So let's say the current flowing through transistor 1 is I1 and current flowing through transistor 2 is I2. So what will be the relation between I1 and I2?
Ma'am, ID is
So
equal, same.
same currents, right?
Yes, ma'am. I1 equal to
And
I2.
we call them as like matched transistors. So these two transistors are matched, so they will have same currents flowing through them. So we know that I1 is I2.
If
Now if,
mismatches occur, it won't be equal, no, ma'am.
sorry?
If mismatches occur, mu1 VT, then
Yeah, if
they,
mismatch is there, they won't be equal. So that's why these are matched transistors with all the factors matched. When VGS is also matched, they'll provide you with same currents. Now, we also know that when we observe at this path from VDD all the way to ground, we see that the current that can flow through this path is a single current, right? Because all the components are in series. So, like transistor 3, resistor R, and transistor 1, all of these are in series, so they can carry a single current. Correct? So, how the KVL will look like? KVL between VDD to ground. So, it will look like 2.5 volts equal to, so let's write it as VSD for time being. But if you observe very carefully, it is VSG again. So it is VSG of transistor 3 plus I into R plus VGS of transistor 1. Now here we know that the same current is flowing through all these, like transistor 3, resistor R, and transistor 1, and that particular current is I1, right? So I1 is the current that is flowing through all these transistors. So for transistor 3, for T3, if we write the current, how will we write the current? It is mu P Cox by L. Now here it is WP into VGS, or let's say VSG minus mod VT whole square. Right? This is how we'll write the current. And this current is I1. Now, if you observe very carefully for this transistor 4, your VSG of transistor 3, VSG of 3 is equal to VSG of 4. Again, because of this diode connected configuration, and since the gates are connected, you have same VSG for transistor 3 and transistor 4, right? So what will be the current that will be flowing through transistor 4? The current through transistor 4, let's say I4. T4 carries I4. So how do we write I4? I4 is mu P Cox W mu n Cox W by 2L, where this WP is 21 times of WP, right? So WP into 21 VSG minus VT mod VT whole square. Now here, okay. So we know that I1 is how much? Mu P Cox WP by 2L VSG minus mod VT whole square, right? So I can write I4 as 21 times of I1. Can I write this? Any doubts how we got 24 times I1? By comparing these two, okay? No doubts in this, right? So again, moving on to the circuit. So now we know the current flowing through this fourth transistor is I4. Current flowing through the second transistor is I2, which is I2 is equal to I1. We already know this. Now let's say the current flowing through this transistor is Ix for now. So applying KVL at this A node. So KCL at A. So how will the KCL look like? I4 equal to I2 plus Ix. Ix is I4 minus I2. So Ix is
20 I1.
20 times of I1. Correct. So now we know that the current which is flowing through this transistor is 20 I1. Again, if you observe between your T5 and T6, transistor 5 and 6, your gate is shorted. So definitely your VGS is equal, right? So VGS 5 is equal to VGS 6, which means I5 is equal to I6, simply.
20
So,
I1, ma'am.
so same current will flow through this transistor. So transistor 6 will have I6, which is equal to 20 of I1. Now, if 20 I1 is flowing through this transistor, then what will be the current flowing through the resistor?
20 I1.
Same 20 I1. So I will be 20 times of I1. So the current that is flowing through this resistor is 20 times of I1. Now, what was the question asked? You have to calculate the value of I. So we found out that it is 20 times of I1. But do we know the value of I1?
We need to find out from
We need to find it
I1.
out. Yes. So we wrote this KVL, right? The very first KVL that we wrote down. From there, let's say we have this expression. Yeah, this one. Okay. So in this expression, can we write all of these terms in terms of I1? We can convert all of this expression in terms of I1, right? So let's say I1 is mu p Cox Wp upon 2L Vsg minus Vt whole square, and also I1 is mu n Cox Wn upon 2L Vgs minus Vt of whole square. So from here, we'll get these terms as I1 and like in terms of I1 and I2. So we'll get a single equation in terms of I1 and I2, correct? So that is like a way to solve. Another way we can solve it is we have to find this current, right? So how can we find this current? And if we talk like, let's say we want it in another way. Is there any other way that we can find the currents? Yes, somebody was saying something.
Excuse me, ma'am. Can you please repeat the thing I lost in between from this W where we had taken IX kind of current?
Huh?
So,
Yeah,
so,
this IX current.
so this IX is flowing through both branches. Like I have lost in between. Why it
No, no.
is?
So see, what I said is like I4 is coming from your transistor 4. I2 is flowing through your transistor 2. Okay. We found out that I4 was 21 times I1 and I2 was equal to I1.
Hmm.
And there is another branch which is connected. So definitely a current will flow through that branch, right?
Yeah,
We
yeah, yeah.
don't know what that current is. So we named it as IX.
Okay,
So let's
okay.
say it is Ix.
Hmm.
Now that Ix current, how do we calculate the Ix current? So we can simply apply a KCL.
Hmm.
The moment we apply KCL, we found out that the current that is flowing through this or the value of Ix is 20 times of I1.
Mm-hmm.
Now,
Okay.
since transistor 5 and 6 are matched, so same current will flow through transistor 6 as well, and the
Mm-hmm.
same current will flow through the resistor which is above. So I is simply 20 times of I1.
Yeah, yeah. Okay, okay.
Yeah.
Understood. Understood. Thank you.
So that's what I said. So we found out that it is 20 times of I1. Now the task is we have to find the value for I1. So what is the best way that we can find the value of I1? So one way that I said was like let's write a KVL all the way from VDD to ground, which is 2.5 volts equal to VSG of third transistor plus I1R plus VSG of first transistor. Now this VGS of first transistor. So we don't know the values of VSG and VGS, but we know that the current flowing in that branch is I1 only. So what if I say like okay, let's write VSG. So this is 3, this is 1. VSG 3 is I1 into 12 by mu p Cox WP root under plus VT. So I can write my VSG3 like this, right? Similarly, VGS1 can be written as I1 into 12 upon mu n Cox Wn plus Vt. So if we substitute these VGS3 and VGS1 in our expression of this KVL expression, the whole expression will turn out in terms of I1. Only one variable will be remaining, which is I1. And when you solve that, you can finally find the value of I1, and hence we can find the value of 20 times of I1. So can someone quickly solve this and let me know what is the value of I1 that you are getting from this equation? Yes, what is the value of I1 that you are getting from the equation? It is like 2.5 into UPC also I do, right? Wn is 10 micro, Wp is 20 micro.
Ma'am, it would be 2 times of I1, 2L, UN, CVOX, WN plus 2VT.
Sorry?
It would be 2 times of I1, 2 into L, V1, CVOX, W by N, ma'am. Where WP and WN, there is a relation given in the question. I substitute these parameters.
Right.
V1, CVOX, where they vary. So by substituting, I get 2 times of
Yeah, so it will be like if we observe very carefully, mu n Cox Wn by 2L and mu p Cox Wp by 2L will actually be equal.
yes, ma'am.
Yeah, because of the given values. So we need not even go for this. Like we can simply write it as like single values. So it can be simplified as
2.5.
2.5 equal to 2 times of VSG plus I1 R. So which is like 2 times of root under I1 into 2L by
We
mu n
forgot to substitute
Cox
2VT.
W
Okay,
plus
okay, yes.
VT plus I1 R. So from this also we can get it. So only one time calculation is required. So here this needs to be solved for the value of I1. Yes. So when we solve this expression, the final answer that we get for I, which is 20 times of I1, is 2.558 2.558 milliamps. Yes. So this is the value of current that we will get through this particular resistor, load resistor I. Any doubts in this? See, the circuit appears very complex, like it has 6 transistors. How would we solve it? But the analysis is very simple, especially when they're like matched transistors and when they're ideal transistors, especially. So the analysis becomes very easy. So hope there are no doubts. Let's move on to the next problem. So it is again a similar kind of problem. In this problem, we have like A, B, C, D. The widths are denoted in terms of A, B, C, D. So this is 1 time, B is 4 times, C is 3 times, and again D is 1 times. And we have to find what is the current I copy for a given I reference of 553 microamperes. So the current flowing through this is I reference. So what will be the current that is flowing through this AW1 transistor? Let's name them as TA. So the current flowing through TA is IA. What is IA? What is the current flowing through IA?
Difference, ma'am.
Same I reference, right?
Yes, ma'am.
So IA has current flowing through it as IREF. Now, next, since transistor B is connected to transistor A, so it has same VGS.
But W is different.
But W, yes, so definitely the W is different. So it can be written as mu n Cox 2LWB VGS minus VTH of whole square. So if we observe very carefully, it is 4
4
times
times
of
of I
A.
reference.
So IB can be written as 4 times of IA, that is 4 times of IREF. Right? So this is what we have for IB. Now if you observe very carefully, the current that is flowing through transistor B will, the same current will flow through transistor C also. Correct?
Because they are in series.
Yes, since they are in series. So IC is equal to IB. But here there is a difference in
W.
the W's. So here W needs to be considered. So when we try to consider W, or we can directly say like IC equal to IB irrespective of change in W because they are in series. So anyways, the current that will be flowing through like transistor B will definitely be flowing through transistor C. There is no other way around. Now, when we again come to transistor D, so for transistor C and D, we again have VSG of D is equal to VSG of C, right? So that means the current that will be flowing through, let's say, the transistor D is mu P Cox WB by 2L VSGD minus VT whole square. The current that is flowing through transistor C is IC, which is mu P Cox WC by 2L VSGC minus VT whole square. correct? We know this current is equal to IB, which is 4 IREF, 4 times of IREF. And we also know that this WC is how much? 3 times of W, right? Yes, so this WC is, let's say we denote it as W2. So these are like same W2, W2 or WP, WP. So mu P Cox 3 times of WP by 2L VSG minus VT whole square is 4 times of IREF. We know this. So if I say let's write mu P Cox WP by 2L VSG minus VT whole square will be how much? 4 by 3 times of IREF, right? Now coming to this transistor ID. So here we have already written like it is mu P Cox WD by 2L VSGD minus VT. Here WD is how much? It is 1 times of W2 or 1 times of WP. So we can write it as mu P Cox WP into 1 by 2L VSGD minus VT of whole square. So we have already found out the value for mu P Cox WP by 2L VSG minus VT whole square, right? Which is 4 by 3 IREF. So ID will be 4 by 3 times of IREF. Any doubts in this? So the value of ID will be how much? 737.33. Yeah, 737.33 microamps. So any doubt in this, like how we solved this problem? Any doubts in this?
Yes, ma'am.
What is the doubt?
How have you written VGSD equal to VGSC? I don't
V
understand.
VSG.
Sorry.
Source, drain, gate, source, drain, again gate. So if you see the gate are shorted, right? So whatever is the gate voltage for transistor C will be the same gate voltage for transistor D, right?
Okay, okay,
And
okay.
since source is like VDD, so source is also equal. When VGs of both the transistors are equal as well as VS of both the transistors equal, so VSG will be also equal for both the transistors, correct?
Okay, okay.
And we already know that for saturation current, the only voltage that we require in case of an ideal transistor is VSG or VGS, right?
Yes,
So that's why we are only focused on VSG or VGS to solve the problems. Is this clear?
yes, ma'am. Thank you.
Any other doubts? Any other doubts? Okay, so let's solve this problem also. In similar terms, here again IREF has been given. You have to find I copy. And here again the factors have been changed. 8, 7, 8, 8, 7, 8, 1 and 6. We have to find the value for I copy. That's the current. So yeah. How will we start? How to start for this problem?
First, we need to calculate the current across A transistor, ma'am.
Transistor A,
It is
right?
8
So
times
let's
of
write,
I
yeah.
reference.
Will it be 8
Yes,
times of I reference? Will it be 8 times of I ref
Yes,
length?
ma'am.
Why?
Because with is given as
Width is given as 8 times. So will the current through the transistor becomes 8 times?
No, current will be IREF.
Yes. The current will remain the same because it is a series transistor, like so the transistor is in series with the current source. So the same amount of current will flow. So that means here we can write like mu n Cox 8 times of W1 by 2L VGS minus VT of whole square is IREF. So which actually converts it to mu n Cox W by W1 2L VGS minus VT of whole square is IREF by 8. Correct? Okay. Now next, what else can be observed from this? So transistor B, A and C, all of them have same VG. VGA equal to VGB equal to VGC. And S is grounded for all the conditions. So which brings us to the conclusion that VGS-A, VGS-B and VGS-C are equal. Correct? Am I right?
yes, ma'am. Yes, ma'am.
Correct,
Because
no?
they are connected and common source.
They are connected with a common gate voltage, right? So the same
Common.
amount of current will flow through all these transistors?
No, ma'am.
No. Why no? What
Because
about
because
A and C?
because A and C will flow same current, ma'am.
Yes.
But C will not flow the
B
same
will
current.
not have the same current. Correct. So IA is equal to IC. But what about IB? So if I'll write IB, how can I write mu n Cox WB by 2L VGS minus VT of whole square. So IB is mu n Cox 7 W1 by 2L VGS minus VT of whole square. So IB will be 7 by 8 times of IREF. IC is IREF. Okay. So now here we have to find the value for uh, I copy, the current that is coming out of this transistor, right? Or this node, this particular output node, let's say. What is the current that is flowing through IC? Yes, what is IC?
Same of IREF.
Same of IB or IA. Yeah, which is IREF.
IA.
So this is IREF. This is what we know. Now, if we find IE and we subtract IC from IE, we can get I copy, right? Because I copy can be written as IE minus IC, correct?
Yeah.
So if we find out IE, we can simply subtract these two and we'll get the I copy. So now how to find IE? So we found out that IB, the value of IB is already found out, right? Yes. We already know IB. So whatever current is flowing through IB, the same current will flow through ID, correct? IB equal to ID. Any doubts in this? Because they are in series again. Current in series will remain constant. So IB is equal to ID. So ID is 7 by 8 times of IREF, which is 7 by 8 times of mu n Cox W1 by 2L VGS minus VT of whole square. Now this has become, ID has become 7 by 8 times of IREF mu p Cox W2 by 2L VSG minus VT of whole square. Correct? Writing it from a PMOS point of view. So this is the value of ID that we are getting. Again, for this particular transistor, if you observe that the gate voltage has been shared and source is also shared, so we have same VSG for transistor D and transistor E. So VSG of transistor D is equal to VSG of transistor E. So if I'll write IE, how will I write? It is mu p Cox WE by 2L VSG minus mod VT whole square. And WE is how much? It is 6 times of W2. So IE is mu p Cox into 6 W2 by 2L VSG minus mod VT whole square. So IA is equal to 6 times of ID, correct? Because if I remove 6, other than that, everything is similar to ID, right? So it is 6 into 7 by 8 times of IREF. Now we have to find I copy. And we already know I copy is IE minus IC, which is how much was IC? It was IREF. So 6 into 7 by 8 times of IREF minus IREF. Thirty-four by 8 times of IREF is what we get for I copy. So I copy is how much? 34 by 8 into IREF was already given. IREF was 524 microamps. So which turns out to be 2227 microamps. Any doubts in this?
Can you please count?
Sorry?
Excuse me, ma'am.
I have a doubt that why we are saying IA equal to IC, like IB is not there.
Okay,
IA.
so see, IA, like VGS is same for A, B, and C. That you agree, right? But when
Yes.
we talk about currents, what all a current includes, it is mu n Cox W by 2L VGS minus VT whole square. Correct? Now, let's say VGS is equal for all transistors. But if W is different, can we say it will have same current?
No.
No.
No,
No.
right? So that is the reason we didn't say that IA is equal to IC, like IB. We said IA is equal to IC. That is because their W is already matched. Mu and Cox by 2L is same for all the NMOSs, right? So what are the factors which are actually changing is W and VGS. Now, if for let's say two different transistors, your W is same as well as your VGS is same, they will carry same current. But if any one of these factors change, your current will definitely change. So here for transistor A and C, they are perfectly matched with respect to W as well as with respect to VGS. So that's why we said W is equal to IA is equal to IC. And then we calculated like, okay, what will be the value of IB? So why we needed IB? Because we wanted to calculate the IE current. And to get the idea of IE current, we need to have the idea of ID current, and we'll get that idea from IB current. So that's why first IB was computed. From there, we found out ID, and from there, we related IE. So that's how we move forward. And for IC, simply since these both transistors were matched, transistor A and C, so we simply equated them. Is this clear? Any doubts?
Yeah, understood.
Understood? Okay.
Yeah.
Shekhar,
Yeah.
yeah.
What is these factors 8, 7, 8, 1, and 6 all about?
So these are width factors. So
Okay,
let's
these are
say,
width factor.
yeah,
Okay.
yeah.
Okay,
So,
okay.
like,
So width is compared, they are compared to each other. And how you compare 8, 7, 8, 1? 8 means equal to 8. That means A is equal to C, correct?
so yes,
And then A and B are in the ratio of 8 is to 7, correct?
7:8, yeah.
And so is the A and D, which is in the ratio of 8 is to 1, correct?
Uh, but there we cannot directly say that way. Yeah, we can say it, but it's just that one is an NMOS, another is a PMOS, right?
Yes.
So I denoted it in terms of both, but it's better to write your current ID in terms of PMOS, because
Okay.
your IE will also come in terms of PMOS. So it will be easy to relate, because mu and Cox W by L, or mu and Cox by 2. Let's say we are considering this factor, mu and Cox by 2 and mu p Cox by 2. There is a possibility, and most of the times it is the case, that mu and Cox by 2 is never equal to mu p Cox by 2. So we cannot directly write from there that okay, the currents are equal, but we know that since these are in series, like transistor D and transistor B are in series, so the same current will flow. But these currents can be represented in their own parametric terms. So like for ID, I can write it in terms of like P transistor, and for IB, I write it in terms of N transistor. And that's what I did over here. So I knew that ID, what is the value of ID? It was 7 by 8 times of IREF, which is same as your IB, correct? So that's why I wrote it down like this also. But I know that my ID transistor is a PMOS transistor.
Yes.
So why don't I write it in terms of my PMOS transistor, current in terms of PMOS transistor, like? So I'll get like mu P Cox WD by 2L VSG minus VT whole square. Correct? Now,
Right.
since we have got this and we know WD is W2,
Yeah.
because the factor was 1.
Okay.
So 1 times of W2, so WD is equal to W2. Now what I did, I wrote down my IE in terms of, again, it's IE as a current equation for IE.
So primarily, ma'am, you are referring to the width only. I mean, no other
Yes.
factors really contribute here.
Yeah. So here, see, that's what I said. These current equations, what are the two things that will actually affect? Because it is said that all the transistors are matched with respect to mu p, Cox, mu n, Cox. These are matched. So what are the things that will actually affect your current is width and gate source voltage and your width. Lengths are also considered to be same, equal.
Okay.
So that's why
So,
we are only considering the gate source voltage and the width.
okay.
And we are
So
solving.
in this case, particularly width is quite critical in the respect to each other. I mean, that's what you are
Yes.
trying to say.
Yes.
Okay. Thank you, ma'am. Thank you.
Yeah. Any further doubts in this type of problem? They might appear very critical because of the number of transistors. We can have 10, 12 transistors also, and we can find the currents in the last branch through this mirrors.
Ma'am,
Yeah.
that E and D are the mirror image of each other, correct?
E and D are mirror image of each other. We cannot say it like that because current is not being actually mirrored over there.
Okay.
When we say it is mirror, that means, let's say
Same
I
current
current
flow
is
through it.
same current needs to flow through them. And when
Okay.
that will happen, when your width factors are same. So if
Okay,
both
so
the sorry,
yeah, so is the C and B, ma'am, isn't it? C and B appears to be similar, but they are not actually identical. The current may be different. I mean, between C and B, because C is same is applicable to E and D, so is applicable to C and B. Correct?
yes, yes.
Okay.
So we
Thank you, ma'am.
can
Thank you.
say that these particular circuits, so if I talk about, let's say, a particular region or a particular segment of the circuit of, let's say, E and D. So here, what we can call this particular segment as, we can call it as current multiplier, because
Okay.
current gets multiplied, right?
Mm,
Now,
mm.
if I want to get a mirror circuit out of it, then what I need to get? I need to get same currents in both the branches.
Okay.
So
Okay.
if we get the same currents, then it is a mirror circuit. If we
Okay.
get a factor of it, then it basically acts as a multiplier or divider circuit.
Okay. Right. Right, ma'am. Thank you.
Yeah, that is
It's
the only
exactly
difference.
replica of this if it is a mirror image in all identical parameters. Correct, ma'am?
Yeah, everything is, if everything is identical, your width is identical, gate source voltage is identical, definitely same current will flow through your both
Okay.
the branches, right?
Then
So
only
it
you
is
can call
mirror.
them a mirror images.
Yes, yes. Then it is mirror.
Otherwise, yeah. Otherwise, it's a factors which comes into picture.
Yeah, so it will give you in factors of the widths, ratio of the width. So
Okay.
it will become like multiplier, divider,
Yeah. Yeah.
that type of circuit. So
Yeah.
current will not match. Yeah.
Thank you, ma'am. Thank you.
Any other doubts? Is this clear? Now, can you solve whenever you see these type of mirror circuits and you are asked to find, okay, first branch has this much of current, what will be the current branch? Can you solve these type of circuits?
Somewhere
Which question?
this question.
This particular question, where didn't you like follow? Where you could not follow?
After finding IA,
IA, yeah. Okay, so it's like very beginning. So let me reiterate it again. See here, what we said, IREF is flowing through this first branch, correct? So that same current will flow through this transistor A, correct?
yes, ma'am.
So IA is equal to IREF, correct?
Yes, ma'am.
Now, your transistor A, B, and C have same VGS because gates are shorted, right?
Yes, ma'am.
So now gates are shorted, you have same VGS. So if I have same width W, can I get same current from these transistors?
Yes.
So what I'm saying is your VGS is equal, VT of all the transistors is equal, mu and Cox by 2L is equal. What is different is W. Now I say ki, okay, for transistor A you have 8 times of W1 as width. For transistor C again you have 8 times of W1 as your width. Will your current be equal in both the transistors?
Yes.
Correct, right?
Yeah.
So that's why we wrote down, okay, IA is equal to IC. So the current flowing through C is again IREF. Are you following?
Yes, ma'am.
Yeah. So now IA became equal to IC. Now what about IB? What will be the factor of IB? So what we are doing, let's simply write down, okay, the current through transistor A, how will you write down? It is mu and Cox WA by 12 VGS minus VT whole square. Now in place of WA, I have replaced it with 8 times of W1, which is WA. So I found out that, okay, for mu and Cox W1 by 2L VGS minus VT ka whole square, the value that I'll get is IREF by 8. Right? Now let's write the current for transistor B. So how will you write? It is mu and Cox WB by 2L VGS minus VT whole square. Now replace your WB with 7 times of W1, which is WB, BW1, right? Are you following?
Yes, ma'am.
Yeah. So we already found out that except the 7, whatever the factor is, it is equal to RF by 8 here. So your IB becomes 7 by 8 times of IREF. Clear till this part?
Yes, ma'am.
Now, if you observe this circuit, your IB, so transistor B and transistor D are connected in series. Correct? This is D, this is B, they are connected in series.
Yes.
So same current will flow through both the transistors.
Yes, ma'am.
So
Yes.
whatever is IB, that same amount of current will flow through your ID, like transistor D. So that's what I wrote down. I said that, okay, IB is equal to ID. I already knew that IB was 7 by 8 times of IREF. In terms of NMOS, the current will come like this. But I already know that my ID is or transistor D is a PMOS, right? So let me write this value and expand it for a PMOS. So how will I write the current equation for PMOS? Mu P Cox WD by 2L VSG minus VT whole square. Is
Yes.
this clear?
Yes, ma'am.
Correct? Yeah. Now WD was how much? It was 1 times of W2. Correct?
Yes, ma'am.
So in place of WT, I'll simply replace it with 1 into W2. Right? So 1 times of W2 mu P Cox by 2L VSG minus VT whole square will give me 7 by 8 times of IREF. Correct? Now again coming back to the same circuit. Here if you observe that the gates are again shorted between transistor D and transistor E. And source is VDD. So again your VSG voltage for both of these transistors is equal.
Yes, ma'am.
Correct? So the moment your VSG transistors are equal, so I can write the current for E as mu P Cox WE by 2L VSG minus VT whole square. This VSG is same as your VSGT, right?
Yes, ma'am.
Correct? Now again for in place of WE, what you will do, you will replace it with E times of W2, which was 6 times of W2. Correct?
Yes, ma'am.
So here you will replace it with 6 times of W2. Now we know that for 1 times of W2, what is the value of current? It is ID, which is 7 by 8 times of IREF. So what will be the value for IE? It will be 6 times of ID, right?
Okay.
So that's how we got the value of IE. Now what was the question? The question was to find what is the value of I copy. How do you find I copy? So let's say if you apply a KCL at out node, so how will you write IC? So IE will be written as IE equal to IC plus I copy, right?
Yes, ma'am.
So I copy is equal to IE minus IC, correct?
Yes, ma'am.
So that's what we did at the end. I copy equal to IE minus IC. IE is here. IC we already know that it was IREF from the very first conclusion. So that's how we got the value of I copy. Is this clear?
Yes, ma'am. Thank you so much.
Okay. So any other doubts? Anyone? Any doubts? Is this concept clear to everyone? Okay, so since there are no responses, so yeah. So let's move on to the next problem. Okay. Now in this problem, it is asked to evaluate the transconductance of the circuit, that is I out, the current through this transistor, by V in, and assume the op amp to be ideal. and R is 16.1 kilo ohms. So we have to give the answer in microsiemens. Okay. So what do you understand by an ideal op amp? What are the properties of an ideal op amp?
Ma'am, input resistance is high, ma'am. Output resistance is low, ma'am.
Yes. Input impedance is high, so this is infinite, almost infinite. So if your input impedance is very high, what is the advantage that you'll get?
So
Input,
there is no drop across it. Internal resistance.
No current will flow through your input
Okay.
terminal. So this current will be zero.
Hmm.
virtual
Correct?
circuit will be, I mean, what and all is possible, ma'am, if input in resistance is high.
So yeah, so whatever the current that is flowing through your input of your op amp will be zero, ideally. What about the output current?
Will be high.
Yeah,
Output
output
current will
current
be high.
is never zero. So output current is not zero. So just please keep this in mind. Op amp always has an output current. Its input current is zero, but its output current is never zero. So yeah, now here what is said that okay, so you have your resistor R 16.1 kilo ohms. For this particular resistor and this particular V in, you have to find I out by V in. How would you find out? So there is another property of an op amp which is known as virtual ground concept or virtual short concept. So whatever is the potential at this particular terminal, the other terminal also attains the same or very close voltage similar to the other terminal. So here this terminal is grounded. So this terminal will also assume a ground voltage. Okay. So the current that is flowing through the resistor R, that is IR, can be written as V in by R. Okay. Now the idea is that okay, this is the current that is flowing through the resistor. But this point is not a ground, like perfect ground. It is just a virtual ground. So current can still pass through that point. So the current that is flowing through this branch will be how much? Current flowing through this branch will be how much? If current flowing through resistance is IR, what will be the current flowing through, let's say, branch A?
V in by R.
Same IR, ma'am.
Same IR, right? Because there is no addition, no deduction in the current. So the same current IR flows through your this transistor 1. There is a transistor 2. Now, there is no information about the transistors, right? Like whether the transistors are like mismatched or matched. So, if there is no information given, we'll consider an ideal case and consider that both the transistors are matched. Okay? So, we'll consider that both the transistors are matched. So, if you observe very carefully, these transistors have same W by L ratio. Also, these transistors have same VGS, right? Because gate is shorted and source is connected to the same node. So your VGS is same, W by L ratio is same. Then the currents that are flowing through these two transistors will also be same. Correct?
Yes. Yes.
So what will be the value of I out? Yes, what will be the value of I out?
V in by R.
Same IR, right? Which
Yes.
is V in by R. So what will be the value of I out by V in?
Mismatches.
1 by R. So what was asked? This is what was asked, right? You have to find I out by V in. You got your I out by V in. Now simply substitute the values 1 by 16.1 kilo ohms. So what is the value of I out by V in that you are getting?
That's 62.112 microsiemens.
Yes, 62.112 microsieverts. Any doubts in this particular question? Yes. Any doubts? Is this clear how we came to the conclusion? Clear, right?
Next topic. Next topic.
Okay. So let's move on to the next topic. So before moving on to the next topic, I want to discuss something. Then we can dwell into the next topic. So just in case if you have any doubts, please let me know. Okay? Please ask. Yeah. So after that, this mirror concept, let's move on to Shekhar.
Yeah, ma'am.
Yes.
This ID for V bias, I mean the first transistor,
Yes.
and V, since bias, these gate voltages are same for both the transistor. Uh, I'm talking about the problem number 8, say the op amp one.
Yes.
Then how
Yes.
you, yes, ma'am, how you calculate that R, R is okay, that is one thing which is flowing through.
So what is the doubt? Like, where is the doubt?
Doubt is, how you arrived at that. See, ma'am, this is the current which is going out of the output of the op amp.
Okay. Okay. So let's reiterate it once again. Okay. So here it is mentioned that assume an ideal op amp. So
Yes.
ideal op amps means IN is 0, I out is not equal to 0, Zn is infinite, and
Hmm.
it will follow virtual short method, like virtual short concept applicable.
Hmm.
Okay.
Hmm.
So with virtual short method, here we see that this is ground, right?
Yes.
So by applying the virtual ground method, I can put a ground over here as well.
Hmm.
But mind you, this is a virtual ground. This is not a real ground.
Hmm.
So that's why let's make it like a dotted ground. Okay.
Okay.
But here the voltage we'll consider to be 0.
Okay.
So the current that is flowing through this resistor will be how much? IR will be Vn minus 0 by R, which
Yeah.
is
That
Vn
is
by
VN
R.
upon R. Yeah. Yeah.
Correct?
Yeah. VN upon R. Yeah.
Now we know that there is no current flowing inside the op amp.
Correct. Correct.
Correct?
Correct. Yeah.
This point is not a real ground, so that your current will sink into that ground. That is also not the case,
Hmm.
right? So this
Yeah.
current will flow,
Yeah.
and this current will reach your this first transistor, correct?
Correct. 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 Yeah.
As your drain current, right?
Correct. Correct. Correct.
Now, what I said that there is no mention about the transistors, whether they are matched, unmatched, about their W's, nothing is mentioned. So,
Mm-hmm.
what we'll consider for our simplicity, we'll say that okay, these two transistors are perfectly matched
Okay.
with respect to their mu and Cox, W by
Mm.
L, everything. Now, what is the only factor that can change the currents through these transistors is VGS, right?
Yes. But they are shorted.
But here also the gates are shorted and sources are shorted to each of these
Yeah.
transistors,
Yeah.
right?
Sources are shorted. Yes. Yes. Yes.
So
Yes. Okay.
same current will flow through the drain
Yes.
of your second transistor as well.
Mm-hmm. That's right.
And
That's right.
that current is I out.
Oh yeah. Okay. Okay. Okay.
Yeah.
Okay.
So
Fine. Fine.
that's
Fine.
how we got I out equal to IR.
Okay. Okay.
Clear?
Thank you, ma'am. Thank you.
Yeah. Okay. So let's move on. Yeah. So till now we observed that okay, there is an amplifier. We provide some input, and if we are in the linear ranges, we get amplified output. Correct? Now, what will happen? Let's say if you have the same amplifier You're giving input, but there is a noise with it. A noise has been added to your input. Now, what do you expect from your amplifier output?
Distortion.
Distorted.
Distortion, right? So, your amplifier output will also have noise component, right?
Yeah.
So, is this noise desirable?
No.
No, and never. We never want noise in our systems. So, is there a case where you can, let's say, your input has noise, but there is a system from where definitely it is an amplifier, okay? Because we are talking about amplifiers, so it is already an amplifier. But we can only get amplified output without any noise. Is there a way possible that we can get an output which is amplified, but there is no noise which is coming from the input? Because ultimately we want amplified output without any noise free signal, right? So this can be
Filter.
attained. Sorry.
It should it be filter?
uh
No, sorry,
Filter.
sorry.
Yes. So no, see, filter is a different thing. Filter, when we say filter, so we generally mean screening, but when we talk about in circuits perspective, filters mean screening the frequencies, right? But let's say you have some high frequency signal which is like having similar frequencies to that of noise, then how will you use a filter to like remove your noise? Right. So to obtain like to solve this problem, researchers came up with something called as differential amplifier. Have you ever heard of differential amplifier?
Yeah.
So what is the
Yes.
idea that you have of a differential amplifier?
Difference between two signals.
Okay, what is the simple differential amplifier that you know? The basic differential amplifier that even BTech students use without knowing that it is a differential amplifier. Or they do know, but they don't know the internal circuits. What is the basic
Op-amp.
differential? Yes, op-amp is a differential amplifier.
Yes.
So what we see as a black box op-amp, it is actually a differential amplifier. And what we will analyze is basically the internal circuitry of op-amp. That is what we are going to analyze in this particular circuit. Oh, something went wrong. Is my screen visible to everyone?
Yes, ma'am.
Okay, I don't know whether my screen. So recording is on. Yeah, my screen went off. Okay. So yeah, the op-amp is a basic differential amplifier. So what is, so we know, okay, we have used op-amp, right? So what is the feature that we get from differential amplifier? Like what are the advantages that we get from differential amplifier?
Difference between two input voltages.
Yes. So difference
Uh,
between two input voltages gets
Around
amplified
this.
and we get the
Yes.
output. But how does it eliminate noise? That is my question. It is simply giving you what? The difference between two signals. That difference is
The
being
common.
amplified.
Yeah.
Yes? Okay. So let's take an example. Let's say there is a transmission line, okay? RC circuits. So there are two transmission lines, similar transmission lines, which are carrying your signals, okay? Signal 1 and signal 2. Considering that these two are in same out 1 and out 2, these two are in same environmental conditions, these two transmission lines will be like will come across the similar output noise, right? If let's say you have like two systems in very similar environments or very same environments, they are placed close to one another, whatever disturbance will appear, it will appear in same amounts in both the signals, right?
Hmm.
So the noise which will be added to this particular signal will be the same noise that will be added to the other particular signal. Okay, so the noise is which is added to first signal, that same amount of noise gets added to the second signal. Now from here you can get that idea. Okay, when you go for a difference amplifier, now let's say this is fed to an op amp with out 1 here, out 2 here. So the resultant input to the op amp will be how much? Out 1 minus out 2. So which is out 1 dash plus noise minus out 2 minus noise. So the noise components get cancelled, correct? And your input will actually be the actual output, like actual input which you wanted. So the output will be the corresponding output, right? A times of out 1 minus out 2. So is this clear? The motivation for differential amplifier, is it clear to everyone?
But ma'am, how is the noise is reduced? Like
Noise is not reduced. Noise is getting cancelled actually.
cancelled the
Yeah. And
by
since
using
the
differential
noises,
amplifier we can reduce the noise, right?
we can eliminate the noise
Eliminate
actually.
the noise, yeah.
Yes. But let's say we can say that we can reduce also, because practically there cannot be same equal noise that is being added, right? Some plus minus would be there. So majority of the noise part will be cancelled, but some mismatch will definitely be there. मान लो यहाँ पे if it was like plus delta in both the sides, so this plus delta factor will definitely remain, right? But major part will be cancelled. So that's why it is said that it reduces the noise, or we can say it cancels the noise. When we say it completely cancels, that means both the noises were same, like equal noises were added, and this is getting cancelled. And when we say reduced, that means okay, there was a noise, like two different noises were being added, but majority of the noise was common in both of them, so it got cancelled and remaining is left, which is very less compared to what was actually added. So in that case we can say it reduces the noise. Is this clear?
Yes, ma'am.
So yeah,
So,
so
ma'am,
that is the idea.
a
Yes.
differential amplifier only means only cancels out the noise, right?
Yes.
Okay, ma'am.
See, we already got amplification, right?
Yeah, yeah.
We can use that amplification concept in differential also. But what was the major problem here? The problem was noise.
Noise, yeah.
So the idea was how to reduce the noise or how to eliminate the noise. So that's where this
Ma'am,
differential came into picture. So
ma'am, if
now,
these noises are at different frequencies, then
sorry,
if the noises are at a different frequency,
huh? Yeah, so you're saying if the noises were in different frequencies. So that's what I'm saying. When we say they are in different frequencies, that means they are two different signals. When I say equal noises, that means they, considering that they are same frequencies and like amplitudes are also same. So that's when they will cancel each other perfectly. But the moment the frequencies are different, that means they are two different signals.
Okay.
Although the amplitudes might be same, but when we say two different frequencies means two different signals. So then they are not same. They are two
Hmm.
different signals. They need to be tackled in two different ways.
That time noise is reduced, not cancelled out totally, right?
Yeah, that time we can say that noise is being reduced, considering that the major portion is common in both the noises. Then we can say that the noise is being reduced. If they are
Yes.
perfectly matched noises, then it will be completely cancelled. As you can observe from this also, right? जो input का expression that I'm writing. From here also it is clear, right? When they are perfectly matched noises, they will completely cancel each other. But when they are mismatched noises, then it will lead to reduction in noise rather than cancellation in noise. Clear?
Yes, ma'am.
Okay, now let's dive a little into how this like differential amplifier circuits look like. Okay, so we know that differential amplifiers have differential inputs. Now, what about the differential outputs? Like whether the outputs are differential or are they single-ended output? So, what do you think? What will be the output? When we say differential amplifier, input is differential. What about the outputs?
Single output.
Single output.
That is the difference between the two inputs.
What
Ma'am,
about
if
if
it
you
is
have noise?
normal differential amplifier, it is dual, ma'am. If you take a current mirror action, then only it will be single output.
Okay, so differential amplifiers can be used in two configurations: single-ended output, double-ended output. Single-ended output structure is known as OTA, whereas double-ended output structure or circuit is known as differential pair or differential amplifier. Both of them can be used. So now let's see, okay, how these circuits look like. So when you have let's draw a very basic differential amplifier. Okay. Yes. Okay. So here, if you observe very carefully in this particular circuit, your yes, in this particular circuit, there are two inputs, right? V1 and V2, and there are two outputs, V0 plus and V0 minus, right? So the input that is going to the circuit is V1 minus V2, and the output that you will get out of this circuit is V0 plus minus V0 minus. Correct? So this is a differential pair or differential amplifier. Now, how your single-ended output circuit will look like?
V naught plus and VB will be shorts diode connected.
Yeah. So here you will have your V naught. So the current, so actually the output that you get out of your OTA is actually a current I. Okay. The output you get out of, so this is an OTA, which is a single-ended output circuit. The value that you actually get as an output is an current. So now when you use a load, so you can get a voltage across it, right? So that's how you can get a voltage from your OTA. Whereas when there is a differential pair, the actual output that you get out of a differential pair is a voltage for double-ended. Clear? Any doubts in these basic circuits? So this is known as a differential pair and this is known as OTA. Now let's understand how it works. So let's say if you, so there are two types of signals that you can give, right? Which is common mode and differential mode. So inputs can be of two types, common mode, differential mode. So what do we mean by common mode? Yes, when we say common mode, what do we mean by that? Which means like V in 1 is equal to V in 2. Both the signals are equal. Then it is a common mode signal. Okay. And when it is set like differential mode, then means V in 1 is not equal to V in 2. So what will happen if you give a common mode signal to your circuit, this circuit?
It is zero.
Considering all the transistors are matched, like all the NMOSs are matched to one another, all the PMOSs are matched to one another, the output that you will get is actually 0. And that is what we wanted, right? We said that, okay, considering that noise is a common mode signal, when noise gets added, we want 0 amplification of noise component. So we consider that noise is always a common mode signal. So that's why this circuit was designed to eliminate the noise. Now, when the signals are in differential mode, you'll get the amplification out of your difference between the inputs. And if you observe if you observe very carefully, this circuit actually might remind you of like CS amplifier, right? Basic simple CS amplifier connected back to back. So that is what actually happens here. So amplification you get from the CS part and noise cancellation you get because of this differential part that you have. The two pairs lead to noise cancellation and the gain you get from the CS configuration. So that is the basic idea. Is this clear? Very basics on differential pair and differential amplifier. For more deep knowledge, you can definitely go and go through the lecture videos at NPTEL. But this is like very, I would say, a very bird's eye view from very top. Like, okay, what we are diving into next. Is this clear? Okay. So now with this information, let's dive into our first problem, which is based on this differential pair. Okay. So this problem, this is a differential pair circuit. Can you observe that? So here, instead of these PMOSs, simple resistors have been used. Ultimately, that PMOSs also act as active loads. So they are also acting as loads only. So here, instead of using active load, we have used like real loads or real resistors over here. So everyone can tell that this is a differential amplifier. Any doubts in this? Any doubts? Everybody can tell, right, that this is a differential amplifier. Now, here, looking at this source, we consider it as ideal current source, okay? So when we say the ideal, that the current source is ideal current source, that means this node voltage not changing. Please keep these things in mind because these are very important. Like, what are the nodes I am talking about, and what are the features of each and every node, because it helps you while solving the circuit. So when I say that this is an ideal current source, then ideal current source means your current is constant through that circuit, and also the voltage drop across that current source will always remain constant, which makes this node voltage to be constant. So this node voltage will never change. So now in this particular differential pair, it is asked that you have to, so there are different device parameters which are given. There is Vt of 0.5 volts, Kn is 4 millisiemens per volt, where Kn is mu and Cox, Kn is mu and Cox, W by L, lambda is 0, and you have to find the differential gain for the circuit. So can we simplify the circuit first of all? Yeah. So can we simplify the circuit first of all? So let's see how can we simplify the circuit. I want to make this circuit as symmetric as possible so that I can analyze first part and I can simply replicate the results for the second part. If I have the symmetric circuit, I can get that advantage, right? So that's why I'm trying to make this circuit a symmetric circuit. So 5 kilo ohm, 5 kilo ohm. Can I write this 10 kilo ohms as a series combination of two 5 kilo ohms? I can write it, right? This is 5 volts. MOS transistor, another MOS transistor, 50 ohm resistor, another 50 ohm resistor, current source 0.8 milliamps, and then minus 5 volt. V into V in 1. Now, first of all, what is asked? It has been asked that you have to find the differential gain. So when it is asked that you have to find the differential gain, that means you have to give differential inputs. Correct? So we already know that V in 1 is not equal to V in 2. Okay? So let's do one thing. Let's write V in 1 as V plus delta V, and V in 2 is V minus delta V. Okay? Now we said that this node voltage VA, and let's write it as V naught. So we already said that VA is not changing. VA is fixed. Now when VA is fixed, for these two transistors T1 and T2, if you observe very carefully, for T1 your VGS has actually increased, right? Can you observe that? For transistor T1, your VGS has increased. So if your VGS has increased, it will increase your current ID1. So it will increase the current your ID1 here also, which is I plus delta I. And similarly, here your current ID2 has reduced. So it will be I minus delta I. So similarly, here we will have I minus delta I. Why I can write it like that? Because we know ID is mu n Cox W by 2L. VGS minus VT of whole square. So if I can write, so ID is directly proportional to VGS minus VT whole square, or I can write it as ID directly proportional to VGS. So I know that the moment VGS will increase, my current will increase. The moment VGS reduces, my current will reduce. Clear?
Ma'am,
Yes.
how are you saying VGS is increased
Because I'm saying that I am providing an input V in 1 as V plus delta V, and I am providing V in 2 as V minus delta V, because I want to give a differential signal, right? Where V in 1 and V in 2 are two different signals which are not equal. So inputs are in my hand. So
Okay, ma'am.
for my
Like,
analysis, I am providing these inputs, and I'm analyzing, okay, what will be the gain that I'll observe.
okay,
Okay.
ma'am. Need to clarify, we had seen that the current can mirror, which means that the current input current can also be equal to output. Uh, what about the voltage in mirroring, ma'am?
Voltage mirroring. So how would you say that voltage is being mirrored? Okay, let's say I have two transistors, right? Let's remove this. And these are connected to ground, yes.
Do you work on FinFET and gallium nitride also, ma'am, in the same manner in your research?
No, I don't.
Okay.
I work on 2D materials. So yeah. So you were talking about, okay, let's say, will there be any voltage mirroring in that case?
Yes, ma'am. Yes.
Uh, okay. So let's say the current is ID flowing through this particular transistor. Since the VGS is same, both the transistors are perfectly matched, and I'm stressing on the word matched. Okay. So if both the transistors are perfectly matched, here also I'll see the same current ID flowing through the transistor. Correct?
Yes, yes, ma'am.
So whatever is the current that is flowing through this transistor, so in this we know that VGS of the transistors are equal, currents are equal. What about VDS? Can I say my VDS of both the transistors are equal? So when we say that both the transistors are matched and they are carrying the exactly same current, practically speaking, when will you have exact same currents flowing through two transistors?
Same voltage and same
Same
parameter.
voltages, and same parameters. And when we say voltages, ideally we should only consider VGS. But in practical scenario, your
Channel.
VGS as well as VDS should be equal to have equal currents. So if you say that there are two branches which carry like same current in practical scenario, the currents are exactly same, then I can also say that my VDS1 is equal to VDS2. Because in practical case, I is a function of VGS, also VDS. Correct?
Because of channel length modulation, no?
Yeah, because of channel length modulation. So here we can say that, okay, the mirroring is taking place in voltage also. We can say it that way, right? So yeah, in that sense, we can say, okay, it is like also leading to the mirroring of voltage. But ideally, since we consider for analysis that these transistors are ideal transistors, so we don't consider the effect of VDS. But practically speaking, if two branches have same currents, then that current need to be a function of VGS and VDS both. It is very important to consider both of these like voltages. Is this clear?
Yes, ma'am. Ma'am,
Okay.
but they are connected in series, so will there be any change in voltage across them? Because
Where are they connected in series? Which one is connected in series to which?
it's two transistors.
These two are connected these two are connected in parallel, right? For transistors, when we say series combination, that means source drain configuration. Okay? Or for P and N, that will be interchanged. When gates are connected, they are not considered as series, rather they are considered to be parallel.
Okay, ma'am. Then when do you say the transistors are connected in series?
So when we say the transistors are connected in series, so let's say this is a series combination, right? This is a series combination. Now let it be a PMOS, NMOS, or a PMOS, or PMOS and NMOS, NMOS. It can be anything, right? But from VDD to ground, they are connected transistor by transistor. So this is series, correct? So the basic concept of series and parallel. In series, the current remains constant. In parallel, the voltage remains constant. So that is the basic idea. Here also we use the same idea. So if like there are two set of transistors, okay. Here again it is VDD and this is ground. So what will we call this pair? So in this particular combination, it is series. But when we look at this whole of like whole circuit, so it is like for this it is series. For this total, it is like one series combination is in parallel with the other series combination. Correct? So the basic idea of series and parallel that we use in normal circuit analysis, that is what is used in case of transistors as well. Hope this is clear.
Yes, ma'am.
Okay. So yeah, where were we? So we were talking about this matching, right? Yeah. So here the voltage has been increased, so which will increase basically the current in that series combination. Also, this side the voltage has reduced, so it will again reduce the current in the series combination. Now, if you observe very carefully, the transistors, sorry, the resistors which are present over here of 5 kilo ohm and 5 kilo ohm, and this V0 voltage. So there are two different behaviors that are going on both the sides of these both the half circuits, right? In this half circuit, the current has increased. In this half circuit, the current has reduced. But if you observe very carefully, these two resistors are in series. So is there a way that with this changing behavior of IV like currents, this can also have the same current flowing through both the resistors of 5 kilo ohm and 5 kilo ohm, and also that uh, so we know that these 5 kilo ohm and 5 kilo ohm are in series. That means one single current can flow through these both 5 kilo ohm and 5 kilo ohm resistors. This is clear to all of us, right? Is this clear to all of us? I'm talking about these 5 kilo ohm resistors. These two are in series. A single current can flow through them. But now when we observe the behavior of current, which will be, let's say, entering this node and which will be entering this node, these two are very different and actually exactly opposite to one another, right? So how is it possible to handle two different currents entering from two different nodes in a series combination? It can be only handled when there is a ground over here, right? So let's say if there is a ground at V0 point, then whatever current is entering from both the nodes can simply go to ground, correct? So that's how this circuit can be handled without any discrepancy with series and parallel combination concepts. Clear? So now what we will do, we'll try to analyze the half circuit. So we'll divide this circuit into exact halves and we'll try to analyze the circuits. Since we want what we want, differential gain, right? So differential gain will come from AC analysis. So we need to perform the AC analysis of the system, of the circuit. Now, if we go on analyzing this whole circuit's AC analysis, it will be very critical. So that's why what we do, we simplify the circuit and we only solve the small signal or small signal analysis for half circuit, and then the same will be applied to the other half of the circuit. So that is the idea. So now if I draw the half circuit for this particular circuit, how my half circuit will look like. It is 5 kilo ohms. VDD node will be grounded. There is another 5 kilo ohm and there is this V0. We came to the conclusion that that node will also be actually grounded. Now there is a transistor T1. With this transistor there is a resistor of 50 ohms. And I earlier said that this node is not changing. VA is not changing. It is constant. So that means it is also a DC node again. So it will be AC grounded. So how does the circuit actually look like? So this is actually appearing as a source degenerate CS amplifier, correct? If you look at this half circuit, can you relate it with the source degenerate CS amplifier small signal model? Hello, am I audible? Are you following?
Yes, ma'am.
Correct,
Yes.
right? So we can relate it with the source degenerate CS amplifier circuit. So now what we do, since we already know that this is a source degenerate CS amplifier circuit, how do we write gain? Gain for the source degenerate CS amplifier? GM into Z out, correct? Minus GM into Z out, and which is so the gain that we get for source degenerate circuit is minus RD parallel RL. So this has already been solved in the um, lectures, and also you know how to solve for a source degenerate amplifier and get your gain, right? So this is the same thing. So we'll simply put the values for RT parallel RL, which is 5 parallel 5 kilo ohm by 1 by GM plus 50 ohm. Now we have to calculate the value for GM. Yes. So GM, we know it is root over 2 mu n Cox W by L into ID. Now here, if we observe this particular circuit, so this 0.8 milliamperes current is a constant current. And when we say that both the circuits are matched, so this is a DC current, so this current will remain always constant. So that means each branch carries half of the current. So the current that is carried by this branch is actually 0.4 milliamperes. And again for this branch is 0.4 milliamperes. So actually the value of ID is already known. So ID is 0.4 milliamperes for one transistor. So GM is 2 into Kn
Ma'am,
means yes.
ma'am, what is the purpose of zero point 0.8 milliampere current source, ma'am?
So this is actually defining what will be the current that will be flowing through your circuit. So that this actually tells you the total current that can flow through your circuit. So it limits your current in the circuit. That is the idea. Your current cannot go beyond 0.8 milliamperes.
Oh, fine, fine.
Yeah, it is always fixed at 0.8 milliamperes. Okay.
Ma'am,
Yes.
so we are considering that half circuit till VA point only, or
Yeah, so see, after VA, what is there? It is a current source, right?
mm-hmm.
But at VA, I already said that the node voltage is not changing. So when we are doing AC analysis, what is important to us is all the AC nodes. But beyond
Mm-hmm.
that, since there is no AC node, so I've already
Mm-hmm.
grounded it, right? AC ground karne ke baad, there is no purpose of that. So we are using
Mm-hmm.
till that point.
Okay, okay,
Yeah,
okay.
that is the reason.
Okay.
So Kn, which is mu n Cox W by L, was already given to be 4 millisiemens per volt into 0.4 milliamperes. So the GM that you get, it turns out to be 1.789 milliamperes per volt, and AV turns out to be 4.105 minus 4.105. So this is the differential gain that we get out of this circuit. Clear? So there's another thing. When we talk about differential pair, as we said, we have both differential gain common mode gain. Differential gain is denoted by AD, common mode gain is denoted by ACM. So there is a very critical figure of merit that needs to be considered in case of differential pair. It is CMRR, which is known as common mode rejection ratio. So the ultimate purpose of your differential pair is to reject the common mode signal. The best differential pair is the one which can reject the maximum common mode signal out of it. But let's say you face the issue, okay, we are rejecting the common mode signal, but my gain is reducing. So ideally your gain should not reduce that much, but still if your gain is reducing, what you can do, you can use another stage after your differential pair, like a single stage CS amplifier or any other stage for gain, how much gain you require according to that, and you can amplify your signal. But noise cancellation needs to be done at the very beginning stage of differential pairs. So it is very critical to reject your noise or common mode signal. So differential pairs are designed majorly for rejection of noise or rejection of common mode signal. Okay. So CMRR is denoted as AD by ACM. Ideally, it should be infinite, considering your ACM is 0. But practically, it is very high. Like a CMRR is from 120 dBs to 180 dBs. In this range, you'll get your CMRRs for your op amps and all differential pairs. So CMRR needs to be very high. Ideally, it is infinite, considering that ACM is 0, and practically it is from 120 to 180 dBs. So yeah,
So ma'am, increasing the CMRR, that means it will reduce my overall gain, the diff amp
No,
gain.
that is not what I'm saying. So what I'm
Okay.
saying is, see, CMRR is AD by ACM. The
Mm-hmm.
question can be, okay, let's say I'm designing an differential pair. I'll increase my CMRR by increasing my AD without considering my ACM. That will be actually a wrong approach. You should improve your CMRR for a differential pair by considering your ACM first. You should get the best ACM out of your circuit. Then you go for like improving your differential gain. For a
Okay.
certain case, let's say you have got best ACM and you reach till a certain point of differential gain. But beyond that point, if you are trying to improve your differential gain, it will definitely improve your CMRR, but you are also seeing like there is your ACM is actually deteriorating. So that is not a good approach. So when you are designing a differential pair, you should first focus on your ACM. You should get the best ACM out of your circuit. That's what I said. And you'll get for that best ACM, you'll get certain amount of differential gain
Okay.
and
Okay.
you'll satisfy your CMRR. But now let's say your signal requires even more amplification because your signal is very small. So in that case, what you can do, you can use another stage, a single stage amplifier or a multi-stage amplifier, and you can further improve your gain, right? You can further improve your gain of the output. But noise rejection needs to be done at the very beginning stage of differential pair. So that is the idea.
Okay. So
Yeah.
means at the first stage of when I'm designing the amplifier, so we should focus more on how I can I mean reduce the ACM, right?
Yes. When you
And
are,
I should
let's
not
say,
worry
designing,
about
yeah,
and I should
when you
not
are
worry about the differential gain
correct, correct.
at
When
the
you
first
are,
stage.
let's say, designing an op amp, okay?
Mhm.
So we always see the op amps in sort of a black box, but actually the circuit which is inside the op amp is somewhat like this. It
Mhm.
is also even critical because all the components are just transistors. So it is made up of all transistor circuit. So there the idea is at the very beginning stage because you can use one differential stage and after
Mm.
that you can use multiple single stages or like cascade or other stages to attain the gain. But for noise cancellation, the differential phase is very important, like differential stage is very important. So first
Okay.
focus on noise rejection through differential stage. When you attain, see, there also you'll have this constraint of CMRR. Anyways, you have to meet the CMRR. So what I'm
Mm.
saying is rather than meeting your CMRR by increasing the AD, you focus on reducing ACM first to attain the given CMRR. Now, in that, you can add multi stages to improve your AD, and finally, you will get op amp, which is which has very good common mode rejection. Also, it gives you very high amplification. So both work simultaneously. So that
Okay.
is the idea. Clear?
And I have, yeah, and also I have one more question. So, in this question, the above question which you have solved,
Yes.
so there you in the input you have used V plus delta V and V minus delta V, right?
Yes. Yes.
So we have common V. So is it a common mode and then delta V and minus delta V
No,
is
no, no.
differential, or what is
ऐसा
that?
ऐसा कुछ नहीं है. So
Mhm.
instead of that, I would have just used, let's say, plus V plus delta V or minus delta V. So it is like whatever was there. See, first of all, you will bias your circuit. Correct?
Mhm.
When I say
Yeah.
differential input or common mode input, we are mostly talking about AC inputs or signals that you provide. But before that, your circuit is already biased, right? As I said, this zero
Yes.
point 0.8 milliamperes is a DC current, which you are actually getting from your biasing. So
Mhm.
biasing is already fixed. Your gate voltages are at certain fixed voltage. Now what we are saying is, okay, if you apply a signal which is in same phase and same amplitude, then it is a common mode signal. Now if you apply two different signals, or let's say to simplify it, let's say your signals are both same, but there is a 180-degree phase shift. then the two signals will be different, right? They're like, one is if one gives you plus 5 volts, other will give you minus 5 volts at the same point. So they are differential mode. So that is the idea that we get from common mode and differential mode. And it is
Okay.
again AC analysis. So common mode and differential mode are AC analysis. Before that,
Okay.
your circuit is already biased with all the DC voltages, and it carries a DC current, which is defined by this current source that you put in the bottom, or you call it tail current source, because in practical or in reality, you won't get a current source over there. You will design this current source using your MOSFET. And there are certain constraints that need to be followed to make this current source as ideal as possible. So that is
Okay.
the idea. Yeah.
And so, like in this example, it is given like to find the differential gain. So, for example, if they ask for the common mode gain, so only
Yes.
difference we will make it
Yes.
both
Only
both
difference.
plus delta V plus
Yes.
delta V will
Both
use.
plus delta V. Both you will use as plus delta V and plus delta V. And then we will solve. And for the common mode gain, the formula is ACM is given by V out upon Vn by 2. So it is like Vn 1 plus Vn 2 by 2 is what we call as Vn by 2. So this is the formula for ACM. Because there are two voltages, right? So you want it with respect to one, so you have to reduce it by half. So this is the formula for ACM. And for differential, it is like, if we go by very basic, it is V out by Vn1 minus Vn2.
Okay.
Yeah.
Uh, uh, I just read in one book so where they were saying whenever we transmit any signal, so what we do, we use let's say if I have any signal one, and in the like in the V in two, which is our the minus terminal of the differential pair, so there we will put the same signal with inverted, I mean kind of 180-degree phase shift.
That's what I said,
Uh,
no? So this is
so
the
but
very basic, to understand it very, uh, like when we say two different signals, so rather than using two different magnitudes, we just played with the phase. If there was
okay.
two other magnitudes with same phase, tabhi you would see V1 minus V2, right? It can
Okay,
be
yeah.
either things. Or
But
you
in the
can
gain, no,
use,
but in the gain we are getting right. Like gain will be A, and then bracket will be V in minus, and because anyway we are taking 180-degree phase shift, so amplitude will be minus minus. It will be plus, right? So it will be double of our gain. Uh, so that I'm not understanding. Is it not giving us a fake? For example, I have one. I mean, signal I'm giving,
hmm.
and at the output it will be gain minus V out plus minus of V out minus, right?
हाँ हाँ हाँ
And I am taking a 180
हाँ
degree
हाँ,
phase
yeah,
shift,
yeah, I
so
got it.
minus
So
with
यहाँ
plus.
पे वो minus का plus हो जाएगा because it
So that
is,
means, yeah, so that means it is giving us a fake information, right? Because let's say my amplitude is 2 volt, for example, and then it will
हाँ
be 2 minus of 2, that means 2 plus 2, 4.
हाँ.
So,
But actually, if you see, your input is also 4, right? Because your input is like difference क्या आ रहा है. जब difference ही तुम्हारा 4 आ रहा है input का, तो वो उसी को
yeah, yeah,
amplify करेगा ना.
yes, yes, yeah, yeah.
Yeah,
Oh, yeah. This I missed. Okay.
yeah.
Yeah, thank you.
Okay. Any other doubts? So if there are no doubts, maybe we can break over here and we'll discuss more on differential amplifiers in next week's session.
Yeah, sure. And also, can in the next session, can we discuss about the current mirror where we had register, right? Where so that we can control our GM. In the lecture, the sir told about that, but I did not have much
Where
clarity of.
here also we have resistors, right?
Uh,
In between. Like in this particular question, we used one resistor. Here also there was this
because
one
in that
resistor.
lecture, Because in that lecture he just told we have the diode connected, and below we will connect one resistor, and using that resistor we can control all the GM of all the MOSFETs, and uh, and that
Uh,
he called as a GM biased current mirror.
okay, so where the resistor is being connected?
Uh, it is with the and also we have a question also related to that uh, in our assignment, which is assignment 9. I mean question number 9 of
Okay,
week 5.
okay. So what is it that is mentioned over there? So see, you got the analysis right, how to do the analysis. How does that matter if you add another resistor? Your rules will remain the same. You simply have to solve it. That's all.
Okay, okay.
Everything,
Hmm.
the flow remains the same, the formulas remain the same. It's just
Hmm.
if there is an another component which is being added, you have to
Hmm.
see how you will tackle it. Now let's say there is another resistor which comes in series in your MOSFET's concept. So you know that the same current is flowing through the resistor, and the drop across that resistor will increase. So the actual drop across your transistors will reduce. So those type of analysis simply you have to use. Otherwise,
Okay,
concepts, whatever the concepts are here, the concepts will remain same. The formulas will remain same. Just you have to see how to tackle these extra components, like how are they appearing in your
okay,
like
okay,
how will you use and solve them,
okay. Actually,
but
in
the
that circuit,
concepts will remain same.
actually in that circuit, the VGS was not different. I mean, it was different. VG
Huh.
was same, and in the source there was one resistor has
Huh.
been
So
implemented,
there
which was
when
changing the VGS.
yes, so there
Yeah.
there you cannot use this concept. Here we are simply
Yes.
saying that VGS is same. So
Yes.
very like many things become very easy because of this VGS equal.
Hmm.
Now the moment VGS will change, definitely your currents will not stay same. The currents will be
Yes.
affected. So that way it will change your analysis.
Yeah, and that circuit he told as a constant GM bias circuit,
Okay.
which will which will uh, I mean control all the GM of the transistor. So that I just wanted to understand,
Acha.
how
So
that
it is
circuit
more
works.
like a source degenerate circuit. एक source
Yeah,
degeneracy
yeah.
वाला जो आता है, so that concept will come into picture with multiple other transistors. So maybe
Okay.
you can analyze that एक एक करके एक एक
Hmm. Yeah.
transistor का how VGS is changing, how VDS is changing. Then when
Hmm.
you know the currents, you can find the GMs, and then you can see okay how GMs are changing, whether they are changing or not, how which factor is affecting what. It is ultimately
Hmm.
about the analysis because
Okay.
you
Okay.
know how things work, how what are the formulas, everything you know. It's just now you have to analyze the things. That's it.
Yeah.
Nothing
Sure. Sure.
different.
I will amend. Yeah.
Yeah, that is the case.
Yeah. Sure. Thank you.
So yeah, if there are no further doubts, maybe we can break over here and meet next week. Till then, have a wonderful week ahead, and see you all
Yeah.
next week. Bye. Good
Yeah.
night.
You too. Yeah. Bye. Bye.
Bye. Good
Happy
night.
Teachers Day.
Ah, thank
Thank you.
you.
Thank you.
Bye.
Just day, ma'am. Bye.
Bye. Thank you.